This meeting is now being recorded.
And to provide a little bit more background on how we got here on this, to get to this webinar, we have, as a community in the Clean Cooking Center, have been working on testing protocol development. A lot of work has been done on testing efficiency, emissions, some on safety as well. Durability testing has been going on. A lot of people have been doing it, including, as reported at a webinar probably around a year or a year and a half ago. It was a WinRock and EPA webinar. But what was lacking previously was a harmonized approach to durability testing. And so similar to what has been done for other testing protocols, the goal really was to have durability testing kind of be integrated together as a single protocol. And so that's where Christian came in at CSU, and then working together with an advisory committee to provide review. This is really a community protocol. The results here that you'll see today reflect a lot of input from a number of organizations already, and this webinar today is to continue that process to seek input a little bit more broadly as well. And so that's the goal here today, to share what Christian and the team of durability testing experts have put together as a draft, and look for people to test out some of these ideas and provide their recommendations based on their experience. And one more comment before I turn it over to Christian, and that is how this durability testing fits in with the broader ISO International Standards Organization process that has been going on. Because we just had our first technical committee meeting for ISO a few months ago in Nairobi, we did want to make sure that while we were waiting for the ISO work to continue and progress, that we continued work on a lot of these areas that needed further development. And so over the last year or year and a half, that's when a lot of this work has happened, and the idea is to really hand it off to the ISO technical committee to refine further and then integrate it with the other standard discussions about some of the other indicators like emissions and efficiency and safety. So that's the context and motivation for some of this work. And at this point, I'm going to turn it over to Christian, who is a postdoc at Colorado State University. He's been working on cookstove testing, measuring and modeling potential impacts of cookstove performance and use. So at this point, Christian, I'm going to unmute you and mute myself, and please take it away.
Good morning, everybody, or I guess morning from people in my time zone. I appreciate you coming to this talk. Let me go back one slide. So this presentation is going to be a really brief kind of intro, and then we'll actually be going through let me went forward again. Sort of details of the different components of the test. One of the things that makes durability testing a challenge is there are a lot of different, sorry, it keeps jumping forward a slide. A lot of different reasons why people care about durability, why they're looking at durability, which means that we were trying to develop a protocol which was useful for a lot of different groups. Now, there are a lot of different ways the durability can be tested and evaluated. Two of the most common are this idea of survey approaches. And I have to thank Christoph from GIZ. I stole this slide from him. The first is survey approaches, where you go out into the real world and you're talking with customers to understand what has worked and what's breaking down and how often that occurs. The second is simulated usage, where in a laboratory you try and recreate the real world. Unfortunately, both of these have some pretty major challenges to them. With the survey approach, you get really good data, but that data can be hard to generalize. Every situation is so specific and unique that it can be hard to take all of these scattered surveys from the field and get really concrete, generalized data or decisions. The systematic approach, while very controlled, it's really difficult to recreate how, sorry, the slides are moving forward without me clicking. The systematic approach gives you really repeatable results, but how you actually tie those directly to real use is challenging. So we're using this approach of targeted durability tests, and the idea behind these is instead of trying to test the entire product in the lab, the entire cook stove, we look at very specific components, testing specific materials, and of course the specific elements of the stove to see how those might fail, so that they can be a little more generalized about where the potential risks for durability are. So we put together a series of 7 tests or so to investigate specific types of failure that we've heard about occurring in the field. The method that we're using actually requires two versions of the cook stove, replicates. Does that test get tested kind of in parallel? The reason for that is that some of the tests are really destructive. We are trying to figure out how the stove is going to fail and what's going to break. And so some tests really do a lot of damage to the stove, so we need 2 sets. And the second reason we need 2 copies of the stove is some of the tests are done on very specific components of the stove, and so we actually take those components out of the stove to test them individually. I apologize about the jumping around of the slides. I'm not sure what's happening there, but we'll try and keep that under control. The approach that we're using to score these results are similar to the safety test. For those of you who may be familiar with the safety test, where it's a numeric score so that we can compare different stove models. And so I'll be talking about this idea of a risk factor throughout the test. The risk factor, the higher the value, the more serious the durability concerns are, or more likely that durability failures are going to occur, that things are going to break down the stove. We have all of these 7 different tests. We add the risk factors all together, which gives us kind of an overall score for the stove. One thing that's different about how we have this durability protocol configured right now as compared to the safety protocol is we're actually doing a low to high scoring approach. And so a really low score, a score of 0, means that with the current test we haven't identified any known durability risks. And the higher the score, the more issues we've seen. Now with a score of 0, that does not mean that there is no risk. What it means is that just with the test as it is right now, we haven't found those problems. So the first step is you really need to look at the stove for failures and damage that's there before you start testing. Things that might have occurred during shipping, things that were not part of the actual test. And once you have that kind of visualization, you've taken notes, taken photographs, you need to figure out what tests need to be conducted. Not all of the tests that we've laid out here may be appropriate for all types of stoves. For example, some of the tests are looking at factors that have to do with coatings or paints that may not be needed to be done for all tests. we've put together as part of the protocol, we've put together some lists and some guidelines to help people understand when they need to conduct different tests. The first one we're going to talk about is this extended run test. The test has two primary goals: determine what temperature the stove is operating at different points, and to look for how high temperature damages or affects the stove. So again, before starting the test, we do a visual inspection of the stove looking for damages. We've also put together some standardized data sheets that we hope will help groups be able to compare data and make sure that all critical components of the test are being conducted. Prior to starting the test, we ask that people kind of make a sketch of the stove and make it very clear where they're going to be measuring the temperature of the stove, just so that in the future, when we're comparing results, we can see if the tests were done in the same way or what the differences are. So after that, a cook pot is put in place and the stove is run for 4 hours. This is used to get the stove up to temperature. An infrared thermometer is used to measure the external temperature of the stove. So that's both the body and the inside surfaces. Included in the protocol, we've outlined some guidelines of how to calibrate and how to properly use an infrared thermometer. And then once the external measurements have been finished, that we've measured the temperature on the outside of the stove, the fire is put out, and we make measurements on the inside. For each of these tests, we repeat it several times to get average results. So the stove needs to cool for a while so we can get some thermal cycling of the stove. And then we repeat the test a total of 3 times. Again, measuring in the same location for each of those tests to get repeatable results. Once all of the tests are completed, for each of the 7 tests, we've put together some guidelines and some suggestions figuring out how to score these risk factors based on observational measurements. Again, I'm sorry, the slides are jumping forward. Or maybe I had animations put in here that I had forgotten about. But we look at things such as discoloration, small cracks, small components that are broken, large components that are broken, and based on these kind of guidelines, you can rate and score the durability risk for that test. The next test is a quenching test, looking at what happens if a hot stove quickly cools, which you would see when water gets spilled or something boils over. This happens many times, when the pot is too full or when you're sloshing the pot around. A pot is put in place. One of the important things that we found is the pot needs to be smaller than the size of the stove, so that after you've run the stove, what we actually do is we pour additional water into the stove, causing the pot to overflow, pouring into the hot stove, giving a large thermal shock to the stove. So the pot that's used needs to be smaller so that it actually pours in. Again, we repeat this several times, with the stove being allowed to cool and to dry between each of the test replicates. And again, a series of scoring criteria have been put together based on damage that we often see. The second, or the third set of tests is actually being done on the second stove copy, and this is the external impact testing. So this is looking for where the stove might be hit, jostled during shipping, accidentally dropped, things like that. We use a 1 meter length of tube to help guide weights, and a series of 6 weights that we drop down to help make the test repeatable. Sorry, the slides are jumping forward really quickly here. To help make the test repeatable, we actually place a ball bearing inside the tube. This allows it to be a really repeatable impact. The tube is placed on an external surface of the stove. The ball bearing is dropped down the tube, so it ends up being trapped between the stove and that tube. And one by one, we start dropping weights down this tube. Those weights will hit the ball bearing, and we will look for damage, for cracking of the stove, or major dents, things like that. Again, a series of criteria that we'd be looking for, things such as chips or cracked coatings, large cracks that will affect the structure or safety of the stove. If the stove was damaged, the test is finished. If the stove is damaged, we go to a lighter weight. So rotate the stove, go to a new component, and test with lighter weights until you find a point where the weights are not able to cause any damage to the stove. And then the score, the risk factor, is based on the first weight at which damage was seen. So for this illustration, it would be at 150 grams. Damage was seen with the 150-gram weight, but not the 100-gram weight. So that was the first point that damage was seen. Similar tests are done with this internal impact, where we'd be looking at what's happening inside the stove. We score these separately, just because the construction of the stove, some stoves may be very strong on the outside, but they're very weak internally. We saw this pretty often with ceramic charcoal stoves, where the charcoal is actually suspended on a layer of clay or cement. So that was very weak, but the inside was actually the outside was very strong, but that internal lining was very weak, which is why we end up scoring these separately, internal and external values. Again, a series of criteria based on at what point damage was first seen on the stove. At this point, we actually, when possible, we found it much easier to take apart the stove, remove components wherever possible, so that we could test them individually. This is especially important for external metal claddings, so that we could test small coupon samples instead of having to test the full stove. It allowed us to do many more tests with only 2 copies of the stove instead of having to use many, many copies of the stove to do these destructive tests. The first test that we'll talk about here is corrosion test. It's a preliminary test to look at how these metals stand up to corrosive environments, which could both come from just the atmosphere, the air, in a humid area, or corrosion from fuels that have a really high salt or mineral content to them. One of the ways that corrosion is typically tested in the laboratory is actually with surface analysis, with microscopes and things like that, which we decided was outside the scope of the current stove's durability test. It's very useful, but we want to make sure that the durability protocol was written in such a way that it was useful and practical for labs of many different ability levels, not just very expensive university-based labs. So what we do is we actually take metal samples for this corrosion testing. We take metal samples from the stove, and we compare those to how they corrode, compare the corrosion of those samples to metals that we know. So we pull metal samples from the stove, and the protocol has it compare to mild steel, galvanized steel, which the specifics for each of these metals is included in the protocol draft, and also compare to stainless steel 304 and stainless steel 409, metals which have better corrosion resistance. A 20 gram per liter salt solution is prepared, and again, the details of this is included in the draft protocol. This test does require an ability to heat up these samples. In the protocol, we've listed out several very economic and easy to get small kilns ovens, or ovens which can be used for these tests. And you also need a humidity chamber, because after doing these corrosion tests, you see results much more quickly when the metal samples are stored in the humid environment. During that first test, that extended run test, you got temperatures for different components of the stove. And so we use that data to understand how hot we should get each of our metal samples to have it be representative of real-world use. The metal samples from the stove are placed in the kiln along with the reference samples, and it goes through a heating procedure. After being allowed to heat and to achieve a steady temperature, the kiln is turned off, the samples are removed, and they're sprayed down with this corrosion solution that we put together, and then it's put into the humidity box. The process is repeated for each of the metal samples. So for many stoves, there are different metal samples. For example, the exterior cladding body of the stove and the fuel grate. So you would want to test each of those metals, which will have a different temperature that they achieve during normal use. So those samples are put into the humidity box, and then they are allowed to sit for 12 hours. Sorry, excuse me. After 12 hours, this process is repeated until a total of 10 cycles have occurred. 10 cycles is not enough to get all corrosion. Some materials will do better and last longer, but 10 cycles do allow you to start to see preliminary corrosion for most metals. The way we score this is by looking at how much corrosion occurs for our test sample. For example, in the test listed here, this sample X, how much corrosion occurs there versus how much corrosion occurs on our reference samples. So we take those, we look at all the samples for that grouping, and then we kind of rank them. Which samples have the most corrosion, which samples have the least corrosion, just purely visually, and the risk factor is based on how it compares to the other known samples. The other thing that this approach allows is it allows some internal checks for labs or facilities that are doing this repeatedly very often. You can actually archive and save your mild steel and your stainless steel and your galvanized samples and make sure that you're getting repeatable results, the repeatable amount of corrosion week to week, month to month, if you repeat these tests many times on different stoves. Again, you look at the kind of scoring criteria, the rubric, and assign a risk factor based on how the corrosion of our sample ranks compared to the known standards. So, for example, in this one, the sample X ranked third, and so it had a risk factor of 1. The next test is the coating adhesion test. Coatings can be very useful because they inhibit things such as corrosion, as well as making the stoves look nice, but many times these coatings are not very robust, and so they fall apart very quickly, which not only hurts the visual components of the stove and can hurt the market perception of the stove, but if it's put in place to inhibit rust, once they start to crack and flake off, they're no longer achieving that. Again, we take samples from the stove. In this case, we need to take 2 samples of each of the coated materials. If the stove has multiple different coatings which are being used, these tests are repeated for each of those coatings. We look at the extended run test at the beginning to determine what temperature the samples should be raised to. And again, it goes back into the kiln where it goes through a heating and temperature soaking process. Once the samples have been heated, they are removed from the kiln and allowed to cool, and we thermally cycle them 5 times. We use what's known as a coating adhesion test. This is based on an ASTM method. So you take the samples, and you actually, once they've been cycled, you cut through the coatings with an X-Acto blade. A ruler should be used to make sure you get a straight and consistent line, as well as it makes it much easier for you to be able to cut deeply through these coatings. We repeat it in a grid fashion, so you get this hash mark shape. There's guidelines in the written protocol explaining how best to do these coatings or these cuts, at which point you take tape. The tape is pulled off, pressed into that hash-marked area, and then the tape is allowed to sit for 2 minutes. This just helps it to adhere a bit. And we then pull off the tape. What will happen for many coatings is the tape will actually remove some of the coating, and you use this rubric and this guideline to help estimate how much of the coating was removed, kind of in these bins. This method is taken very closely from standard ASTM style tests for coatings. And then you would do this again for all the materials and score it based on which material had the worst performance. The last test that we're going to talk about here right now is a material failure temperature, looking at how hot these materials can get before they fail. Understanding how close the stove is to that failure point can understand how conservative some of our tests are. If you're very, very close to that failure temperature, there's the risk that when the stoves are used in the real world, somebody will use them in a slightly more aggressive manner and components will fail quicker. So we pull samples from the stove and we figure out what temperature we achieved during that extended run test. We figure out what temperature that was for each material, and then we start our tests 50 degrees below that target temperature that we identify in the first test. The samples go into the kiln, and we do a thermal cycling process where we allow them to heat up and then hold that temperature for 30 minutes. After 30 minutes, the kiln is cooled and the samples are removed, and we photograph and look for damages to that samples. Again, the first test occurs at 50 degrees C, but we then repeat the test, increasing the kiln temperature by 50 degrees Celsius each test. And we continue that, the test, soaking in the hot kiln, cooling, and then photographing for each one of these temperatures until we get to a point where we deem the material has failed. Fail could mean that significant corrosion has occurred. Coatings have broken all the way off and we're down to the base material. Components have melted. Components have twisted or warped or gotten to a point where they're just not usable anymore. These tests are repeated for each of the components, and then the risk factor is determined by looking at how close normal operation of the stove was to the failure temperature of the stove. Is there a lot of temperature room left? Is there a lot of safety margin? Or is the stove material, or the materials used in the stove very close to their failure point during normal use? And then the risk factor is based on the highest risk factor of any of the components tested. Again, then we add all these up and we get a total score for the test. Again, the approach that's been used is this targeted series of tests looking for specific failures. There's some very nice pieces about that, but I also want to quickly talk about there's a few limitations to it. Some of the very good things about this targeted approach is that it allows users to conduct the test based on what's appropriate for that specific stove, and doesn't require them to run tests if it's not appropriate. For example, a stove with no coatings would not require the coating adhesion test. So for those regions, we don't penalize them for having any failure of coatings or paints. The downside to this approach is you can't take this data and directly relate it to stove life. How long a stove will last, how many years it will be usable out in the field. While that is an important metric, and we're going to continue working on developing those style tests, it requires a kind of a different approach that I think will need to be targeted slightly differently for different parts of the world based on stove design or the type of failures we often see in different parts of the world. What these tests are very good for is identifying high-risk stoves that have known durability concerns. It also allows users and testing facilities to determine what likely failures the stove will see, so that when they are out in the field looking at real use data, they know more specifically what they should be looking for and what types of failures they should specifically be looking for out in the field. Again, this is still a work in progress. But we've gotten some preliminary good results. I'm excited to see the results that other groups have once they start doing some testing, as well as hearing back from groups about what worked in their facility and which components of the test need to be revised in the future. That was kind of a quick overview. Again, I apologize about the slides jumping. I think I had some animations in there from a previous time I gave this, which caused a few difficulties. But I think at this point I'd be happy to answer whatever questions people may have or open up for discussion.
Thank you, Christian. It looks like we already have one question coming in from Jim. Hopefully everyone can see that as well, about whether degradation of performance after the stove is used or over time, is that part of, is that being considered as part of the testing process?
So, formally, explicitly in the protocol, no, we do not have that. We do not have performance tests, durability tests, and then performance tests again. It is one that we do at CSU, and I think it will be a very useful one, but I see that more as individual facilities making that judgment call. I think it is a very useful tool for stove design and stove evaluation, but it's not formally in the protocol as of right now.
And for the participants, please feel free to type your questions into the chat window. I think because of the sound quality, it'll be easier to keep everyone on mute for now. Please use the chat window. And while people are typing the questions in, one question for you, can you talk about the process, like the advisory committee process, and how you did the protocol development and did some testing of the protocol options and down the committee, et cetera?
So we put together an advisory committee. So that committee was generated, and it was all volunteer-based. And that committee was generated by discussions between CSU and Rady and a few other folks trying to identify stakeholders from different groups. So testing labs, stove manufacturers, NGOs, as well as an international component, so groups from around the world. That advisory committee, we had conference calls and meetings throughout the last year, where I would do some work, we'd have a call, and I would get their feedback on if they felt like the tests were appropriate. Did the tests cover the critical types of failure, and was the general concept that we were using for these tests the best path to where we are here and now. It was very useful. It was an approach that allowed some early feedback from stakeholders, which I think helped kind of iron out some of the early issues. In terms of how the protocol was developed as a whole, the first steps that we did is we did a very intensive literature review of durability test methods that are used by different international groups around the world. I'm not sure the best way to share that, but I'd be happy to share that with folks if they would like to see that. It's a database of around 80 to 90 standard test methods for durability. Of course, they're not really geared towards cook stoves, but it provided us with some background and some starting points on how to develop these tests. We did that literature review, did some target tests at CSU to make sure that these tests were feasible to conduct, and then started drafting the protocol. It looks like another question came in. You mentioned you were testing fuels for corrosivity. Are you currently or planning to test any other elements of the impact of fuels on the cook stove? There are other components that could have an impact, such as the fuel physically impacting into the stove, which we tried to capture by that internal impact test, as well as damage from the moisture in the wood, from the wood as you burn it. We do not have specific tests planned for other elements of the fuel, but it's part of the reason we used the scoring method that we did. As additional durability test concepts come up, as the ISO process moves forward, and maybe other components of durability want to be tested, they're easy to add on because each of these tests are done individually. And so all it would be is additional scoring metrics that could be added on. But as of right now, we do not have additional tests looking specifically at how fuels impact the stove. There are other tests going on separate from the durability work that's looking at how different fuel characteristics affect performance, but they're outside the scope of this durability test. A question came in regarding what methods should be used to test cement and mud stoves for durability. In terms of the tests we've outlined here, the specific ones that would be useful are the extended run test, the external impact test, the internal impact test, and the quenching test are the most directly applicable to mud and cement stoves. But there are a number of other tests from that protocol database that I put together that I'd be happy to share with you that have some other targeted tests for those types of materials. They were just outside the scope of the cook stove durability test.
Rainey again. I have a couple of questions for the participants to think about. For people who are at organizations who do testing, I think we would like to make this draft protocol available for further testing and further input. So please connect with us so that if you're interested in doing that, so that we can share materials with you. We're not going to share it more broadly until it's a little bit more finalized, but I think it's certainly a good plan for individuals and organizations to think about and provide additional input now. And so the question for mainly the testing centers is, what are these methods feasible and realistic for the resources we have available? If not, it would be good to get your thoughts on the feasibility of running these types of tests. And for other organizations, the question is whether these methods get at indicators and measures that you are interested in that would be useful for your work. Christian, it looks like there's a question that came in from Carl at LBNL on how on the statistics of the numbers, the sufficiency of the test file, and of how you determine that indication.
Yeah, the sample size and the replicate size, I imagine as we start to get feedback from more and more facilities will change. The N of 3, well, kind of two pieces. For some of them, for example, where there was 10 thermal cycles, things like that, those were based on best practices from ISO or ASTM or ANSI or Indian Institute of Standards, from other protocols in the past that we used their suggestions for best practices. Some of them, typically the ones with the lower numbers, the replicate count was determined from some of our early tests based on where we kind of first saw damage. I think as the number of groups doing these, as we start to get some feedback from some beta testing that other labs will likely do, we'll get a better idea of how many replicates we need to conduct. Fortunately, we don't have a broad enough sample set yet to be able to do rigorous statistics on it. So it's a starting point right now for these draft protocols that will likely get slightly refined as we get feedback from early testers. Which the engineer in me doesn't like that answer. I'm sorry I can't give you a better one, but we just don't have the sample size yet, unfortunately, to be able to do the rigorous statistics that we'll want to do long term.
Thanks, Christian, for addressing some of these questions, and thanks to the participants for the questions that you've submitted. And then we welcome any questions on the feasibility of the testing, the process for the protocol development, or the usefulness of these types of measures for your work. Please keep the questions coming in now. We'll hang online for a little bit longer for any additional questions that come in. Otherwise, please do get in touch with us if you're interested in providing further review of some of these methods as well. The questions seem to have slowed down, so we'll wrap up here and we'll stay online if anyone is interested. And thank you so much for all the participants who have joined in and for all the good questions and comments about this. And Christian, thanks for spearheading this whole effort.
Happy to do it. everybody.
And Christian, it does look like we don't have any other questions coming in. So we can wrap up. Thank you so much.
Yeah, no problem. Let me know if anything else comes in that I need to address in the short term.